Thank you. Yes, I'm Tim Perry. I want to talk about web application security. A little bit of context first. So I work for a company called Softwire. We make products for other people, all sorts of people you might have heard of, like Cisco and the BBC. A lot of these are very big. They have to work. And the critical part of that is that they have to be secure. We have to ship things to people that are not going to lose them loads of money. A lot of this is on the internet now, big web applications, and we're trying to find ways of being better and better at this problem. And this is very much where I'm coming from here. I'm not a detailed cryptography expert. I'm not looking at theoretical issues. I want to look at security from the point of view of building really secure applications, the things we need to know to be able to do this well. I should note before I get too far that we are recruiting in Bristol and London and Bucharest, and obviously you can hire us if anybody's interested in that, and come and talk to me later. But what I really want to talk about here is security. When I say security, I'm talking about people on the internet trying to break your web applications. A lot of people assume that this isn't really that big a problem if you're not GitHub or Google, Twitter, say. But it enormously is. Even in relatively small projects, there is a lot of value in breaking your systems if I can do so easily. If I can if you've got any money going through your system, obviously, if I can take that, that's great. Even beyond that point, though, you can become a platform for distributing malware and viruses. I can start mining bitcoins on your helpfully auto-scaling servers. You can become a really powerful node in the next botnet, whatever. So if I can find an easy way to break your system, there's a lot of value to me in doing that. And because of that, there are quite a lot of opportunistic people just trying to see if there are easy holes in anything. And if you are easily vulnerable, people will spot this relatively quickly, and it will hurt. Bad things will happen that will be expensive and painful and very embarrassing. I'm assuming for the purposes of this, you look something like this. You've written a bunch of code using a web framework, a programming language. You've got a web server behind this, some data stores, and some network infrastructure carrying your requests back and forth. The fundamental thesis that I really want to hit home here is that everything in here is broken. Nothing works. If you look at people like Google and GitHub and Twitter and Facebook, they have teams of extremely good security engineers working on this stuff full time. They are much better at it than anybody here. They fail very frequently, very visibly. Everybody's going to fail. It's going to be a huge mess. Everything you use is a huge mess. It's all a disaster, which is a great start. So this is not a nice place to be, right? This is a difficult, stressful situation. Things are a bit messy. But it means that really the solution to security is not trying to write, not necessarily only, trying to write secure code. That is a very good thing, and everywhere we can do that, that's great. But you have to be prepared for the fact that stuff is going to fail. You have to put practices in place to limit the risk of that happening and the damage when it does happen, and ensure you're in a place where you can recover quickly when things go wrong. And that's what I want to look at today. There's an upside to this initially, which is that by and large, it's not, unless you do something really stupid, it's not going to be your code that's the problem. If you haven't done something stupid, it's going to take me quite a lot of effort to break your site. I'm going to have to put in quite a bit of detailed analysis about your internal implementation, work out exactly what's going on, and then I manage to start stealing a bit of your money, perhaps. And you spot this, and you fix it, and you shut me down, and I'm back to square one. If I can find a hole in Apache, say, the .NET framework, all of a sudden I can break everybody. If even better, somebody else can find that vulnerability for me, and I can just use it. For very little effort, I can break a huge number of things. And as long as you're not Google or GitHub or Facebook, and this becomes more and more of a problem as you become higher profile, but if you're relatively low profile, the vulnerable parts of your system are likely to be the common tools that are big targets and are going to be getting continually hit. And if you have obvious holes in here, this is going to cause a problem for you. This does lead us to one kind of immediate conclusion to start with. And if you listen to nothing else in this talk, if you go to sleep in 2 seconds, do this. Ensure you're in a position where you get security notifications for tools you use. Every major language, every major framework will have a security mailing list that emails out every time major issues come out. Pay attention to that and be in a position to pull down those updates and put that live very quickly. You need to have development practices in place that allow you to make any changes this update is going to require. You need to be able to quickly test and ship stuff to live. You need to have the ops practices that lets you update production at that kind of speed. We've seen customers where it takes 2 weeks to build a release and ship it to production. And within 2 weeks, if there's something obviously catastrophically wrong, and in a minute we're going to see a lot of ways things can go catastrophically wrong, if there's something catastrophically wrong in your system, somebody's going to notice within that time frame, and it is going to be very expensive and very painful This is not that hard to do, but you need to actively be trying to chase this as a goal. So, working down through some common tools then. We'll start with Rails. Any Rails developers in the room? Anybody ever written some Rails? A couple of people, here and there. In the Ruby community, it's quite popular. It takes away a lot of the complexity of building web applications. Within the Rails community, YAML is very popular. It's a data format that looks like this. It's structurally very similar to JSON, but the braces become optional, and you can use indentation instead. On top of that, it's got a bunch of other exciting features, so we can have typed YAML. Here, I tell the parser, when you pass this document, don't give me a tree structure that I'm going to search through, just give me an actual user object. I pass a bit of input that comes in, and I get given actual classes. The parser here is building my code. I can pass a document and get given a thread or a database connection, which is really not necessarily going to be what you're expecting. This could cause a bunch of problems. You can see how there's the start of some security concerns here, but actually it's not that bad. If we look at the internals, what it's actually doing is this. It calls user.allocate. In Ruby, this builds an empty object. It doesn't run the constructor. It makes an empty template object with none of the values set, and then we go through each key and value from the YAML document, and we fill out all the fields for the object. So we're building an object with populated things, but in principle, we're not running any of our code. So this shouldn't be too dangerous. Except it is, because as it turns out in Ruby, you can overload the key equals value operator here, so that instead it calls a method with the key and the value. And if you did this, and you took this key and the value, which potentially come from input anywhere if you're passing random YAML documents, and then you take this key and the value and you do something very important with them, perhaps you put them into some SQL or you eval a string that contains them, then all of a sudden, passing a document can run your code and do crazy dangerous things and break your system. And unfortunately, somebody has done this, and there was a particularly high-profile case in Rails itself. So, named root collection is part of the core infrastructure for routing in Rails. It overloads the key equals value operation here to call this add method. So if I try and set any properties on it, they go straight through to here. And the name and the root, which would be the key and the value from a YAML document, come in, and then the name ends up in this string, which gets evaled. This hash braces is a string replacement in Ruby, so the name ends up in there. And if I can provide a name that terminates this remove possible method expression, puts in a bunch of other code I want to run, and then comments out the rest of this string, I can, by passing a YAML document, run code. You can pass a document expecting to just get given the data of the document, and the document can be running code because you've done this. And a string to do that would look something like this. We put ignored semicolon to finish the previous statement, and then we print hello or do anything else we'd like to do whatsoever. Shut down the server, delete the database, just record every request and send it off to somebody else. Redirect you, instead of redirecting your user to PayPal, redirect them to PayPal and steal all the money there, and so on and so on. You give the server completely to somebody else if you let them run arbitrary code like this. But then we've got this end keyword, which is a completely mad feature of Ruby that for some reason is available and just stops processing completely. It essentially comments out everything in the file after that point. When we replace this string into here, we get this bit at the bottom. Remove possible method ignored, which does nothing. This removes a method that doesn't exist and nobody cares. And then we run our code. So if we can provide a name that looks like this in the process of passing a YAML document, we win. And a YAML document that does that is this. It's very short, it's very terse, and it gives somebody complete control of the server. If I can get a Ruby process with the default YAML parser to pass this document, I win. I can run whatever code I like. I can delete it. I can do anything. There's also, so we've got the key in here, and then we've also got an open struct at the end, and this is just an empty object that gets us through a bit of validation. So this is really bad, okay? This is absolutely not what you want to be happening in data formats you accept. The idea that you could pass a document, that somebody could give you a bunch of data and you could try and read it, and that would delete your server, is absolutely not something you want to happen. So you'd think that people would be quite cautious about YAML. They, for example, would not accept YAML from random people on the internet and try and pass it. But they have, in a surprising twist. And in early 2013, we discovered that this was a feature of Rails, and had been a feature of Rails for quite some time. Anywhere that accepts XML, you can provide a type equals YAML attribute on an XML element, and then you can put YAML inside it, and it gets passed as YAML. So anybody who accepts XML, which by default is every single Rails server to every endpoint, you can send this, and then you can just run whatever code you liked on the server. In January 2013, people discovered this, and all of a sudden, anybody on the internet could send this 7-line request to any Rails server and do anything they liked with it. This was a stressful time for Rails developers. As you can imagine, this causes some problems. This is an absolutely terrible place to wake up. You do not want to be here. They furiously made sure they were in a position to upgrade to the newest version of Rails. Everybody upgraded. They made all the changes in the code required to actually make that work, to test it, quickly got it into production before somebody noticed them and sent this tiny, very easy to send request. And then they started trying to work out how this actually happened, and we started thinking about the good principles that could stop this happening in the months and years into the future. And then 2 weeks later, it happened again. Here, it turns out that the JSON parser in Rails, the, again, one enabled everywhere by default, is not a JSON parser. It's a YAML parser, because they're very similar. All it actually does is assume that its input is totally valid JSON, and then make the tiniest possible transformation to ensure if that were true, it would now be valid YAML, and then it passes it as YAML. And actually, all this is they find the colons between keys and values, and they add a space. And that means if we take anywhere where we don't want a space and we just swap it for the Unicode equivalent, all of a sudden we can just send a bunch of YAML to the server, promise in the headers that it's JSON, and it'll pass it as YAML for us. And again, we take over the servers, and the Rails developers are very upset, and it's a very tragic, difficult time. And then 2 weeks later, it happens again. This was a very difficult time for Rails developers. So this is inside active record, the ORM in Ruby, in Rails. We're defining a blog post model, and we've got a tags field on our blog posts, and we say it's serializable. And what that means is when you save it to the database, I want you to turn it into a string and put that in the database. This, perhaps unsurprisingly at this point, is serializing to YAML. Not a great choice. It's a nice format in many ways, but not for the internet. So we serialize it to a string, we put it in the database here. But this has a bug. If I provide a list for tags, it gets serialized to a YAML list, and that ends up in the database as a string. If I provide just a string for tags, that just goes straight in the database raw and comes back out raw later. If I provide a string that is just a string but contains valid YAML, the serializer is like, oh, great, it's a string, just chuck it straight in the database. And the deserializer is like, oh, great, it's YAML, I'll pass it. And all of a sudden, anything that accepts user input to a serializable field also runs any code anybody on the internet wants to run, which is probably not what these web applications were for. This is a very, very difficult and stressful situation to be in. Everything suddenly has broken on you 3 times in 6 weeks. Everything is falling apart. Very stressful, very difficult, and very problematic. And really underneath the fundamental issue here is just complete failure of any sort of concern about user input. Rails was designed, certainly at this stage, to be as liberal about the kind of input it could accept as possible. It might be convenient to have XML, so let's have XML everywhere. And it might be convenient to have JSON, so let's have JSON everywhere. And it might be convenient to put YAML in our XML, so that would be nice, let's have that as well. And you end up being more and more accepting of inputs. And the more accepting you are of inputs, the more things there are to break. The more different ways I can send you the same message, the more different ways you have to check that it's secure to do so. Especially since nobody needs this to be really, really liberal and gentle. You're defining your API. You can be very specific on what your API accepts. You don't need to be in a position where if somebody sends you YAML, you'll just kind of make that work. That's not something your web application needs to do. You probably don't need XML and JSON on these endpoints. You can be quite specific, and trying to do that will make your system more secure. If you try and limit the input you accept to specific cases that you know are valid and just drop everything else, then you reduce the attack surface, the number of ways an attacker can poke you and break your system. Similarly, there's also an issue here in the kind of understanding of the assumptions between components in this system. The YAML, the JSON parser, is assuming that the input it's being given is safe. It's not validating it or worrying about it particularly. But the Rails developer who plugged that straight into requests was assuming that it could handle unsafe input. There's a mismatch there in the kind of understanding of the security context of the information we're passing in. And similarly, active record is assuming the information it's being given to serialize is safe data to handle, and it doesn't need to be very careful about it. And it's completely wrong. And because of that, things break. If you understand the assumptions that your tools are making about information, then you can avoid this stuff. And whatever you want to do, whatever you do, you don't want to give potentially unsafe input to a tool that is going to assume that it's safe, that's not going to be worrying about it. Let's move on. PHP. Any PHP developers? More? Yeah. PHP is really big. It's the biggest language for writing web applications in the world. It runs Facebook, Wikipedia, WordPress, loads of stuff. It's absolutely everywhere. If in PHP you wanted to create a create user form, you might submit to some code that looks like this. So I've typed in a username, and I've typed in a password, and I submit it. I hit this. I save the username, I take the password and I hash it with a salt, and then I save those all to the database. The crypt function here is interesting. To be able to do logins later, we need to hash future passwords with the same salt and then compare the results, which means we have to keep track of both the hashed password and the salt. But that's a bit of hassle, so the crypt function returns them both together. It returns the hashed password followed by a $, followed by the salt. And you can then pass that as the salt to future crypt calls as the second argument, and it'll automatically pull the original salt from it. This is a bit weird, but very convenient. And this is the recommended way of doing things in PHP. Until recently, this was in the documentation as the standard way of doing login. And the actual login code, after you've created users like this, looks like this. We take the password that we previously hashed, and we're going to use that as the salt. We pass that to crypt, and we pass the new password that somebody's just entered, and then we compare whether the two hashes we end up with are the same. And if they are, you log in successfully. In PHP 5.3.7, a well-meaning PHP developer made this one character change. It is not a good change. This developer did not understand what they were doing here. This was an important update for a security issue, so everybody essentially had to update immediately. There are millions of PHP applications, and obviously people starting new PHP applications and installing the current version of PHP every day. This was live for 5 days. The actual implementation of these is interesting. This is C inside PHP here, and these are two different ways of concatenating strings. That's dangerous in C because you have null terminated strings. Unlike normal languages where you've got the length at the front of the string and you know the length of a string when you look at it, in C you have to just read until you get to a 0, until you find the end of the string, and that makes it very easy to read off the end or write off the end. And this is dangerous, and because of this we have all sorts of ways of trying to deal with this problem. So Encat tries to make sure this is safe by taking a third argument, which is the length of the second string you're going to concatenate together, to make sure that you don't read off that string, the end of that string. So Elcat is slightly different and takes a third argument, which is the length of the total string you're expecting. This is considered more secure because it doesn't read off either string, potentially. Unfortunately, if you pass 1, this means it always returns the empty string. That length includes the null terminator. So here we concatenate the password with a $, and we throw away the password and the $. That gives us this invariant. Every time you hash a password, you throw away the password. If we take the original login code, like so, and we apply this invariant, this becomes this, which becomes this, which is always true. If you updated to this version of PHP and you were following the officially recommended login mechanisms, straight from the documentation, all of a sudden anybody could log into any system, anywhere running this version of PHP, millions of applications, with any password, overnight. Who here has integration tests that check you can't log in with the wrong password? One hand at the back. Well done. This is not good. For 5 days, people didn't even realize this was a problem. But anybody who noticed could just log in as administrator. And there are a lot of people on the internet just randomly trying administrator passwords. And all of a sudden, they were getting a much higher hit rate. This is absolutely catastrophic. But it raises some interesting questions. Perhaps they should have had tests. Perhaps the PH team could have unit tested this extremely unit testable bit of code and checked the results, which is amusing because they did. They have some unit tests that cover this exact bit of code and fail very clearly with this exact problem. Nobody ran them. The developer who made this change did not run the tests. The developer who bundled this change into a release and shipped it to millions of applications did not run this test. And nobody for 5 days looked at the results of these tests or even considered that it was a problem. Perhaps somebody might have reported it. Perhaps the one person at the back here with integration tests that catch this issue might have told the PHP team about it. They did. 2 days before release, against the pre-release version, somebody filed a bug, which is very clear, pointing out that this doesn't work. Because of this, we need to fix it. It's going to be a big security problem. Nobody looked at the bug tracker. Nobody was paying any attention to this kind of stuff, and for 5 days, 7 days after the initial report, this was still live. This is catastrophic. This is exactly what you don't want to happen in your systems. And the things to fix this are not exciting, crazy new things. I'm not preaching anything mad here. Run the tests once. These are basic good practices, basic best practices that we as an industry are very aware of. They're very good, they're very valuable, and we all know are nice things, but we tend to think of them as things that are for developers. They're stuff to make your code more maintainable. These are practices you do because it makes your life nicer, because you can develop quicker, because future you will have more maintainable software to work with. And that's true, but there are a lot of actual concrete business benefits to best practices. The end result will not just come around quicker and be easier to build, it will be a better product. If you follow best practices, you'll build tools that don't do this, and systems, similarly, that don't do this. And trying to pick tools that follow these best practices will also help. If you are considering picking up a new tool, perhaps see if it has any tests. Perhaps check that they pass. This is important, clear stuff that we're all already aware of and that we all know is important, but that doesn't get put into practice in lots of cases. It's very easy for this to not happen, and things go catastrophically wrong when it does. Best practices add direct business value. Jetty. Anybody use Jetty? Nobody. So in the Java community, Jetty is getting quite big. It's an embedded web server that you can drop into a Java application so that you can just run it on the command line. You don't need Tomcat anymore. You don't need these big enterprisey web servers. It's very nice. It accepts HTTP requests, as I'm sure you've seen before. Perhaps they look like this. They've got some headers, some keys and some values, maybe a body. Some of these are secret. This password here is secret. This isn't a good idea. Don't do this. But you might have session keys in here. You might have all sorts of stuff. Some of your request bodies will have interesting things. Perhaps people submit credit card numbers to your application. You have secrets in your HTTP requests. You can send invalid HTTP requests. The encoding rules for HTTP are a bit fuzzy. This doesn't come out very well. That's a registered trademark next to the accept header there. If you try and just send this in UTF-8, say, it's not valid. You're not allowed to do that. That will be rejected. And in Jetty, you'll get an error that looks like this. It's an invalid character. Here's the start of the request. Here's a bit right up to the invalid character and a helpful little arrow pointing out the invalid character. And then here's the rest of the request. And then a long series of zeros. It's a bit weird that we get these zeros at the end. What this is actually printing is the end of the request buffer in Jetty. And this is a problem. This request buffer is reused for every request. If your request is shorter than the request that came before, there will be bits of the previous request left in here. All of a sudden, with a bit of fiddling, we can read other people's HTTP requests. This is quite bad. The actual process to do this looks something like this, and it's sadly gone slightly off the screen there. So we send one request with a secret in it, and then we send a second request, and it prints out a helpful error explaining why our second request is wrong, and then prints a bit of the next bit of the buffer. And we can actually shift this around as long as our request is always getting longer, and do something like this, put in a few extra queues, and we can get the relevant bit. And because of that, we can keep repeatedly shifting it, and we can basically read all of any of the previous requests. And we can do this all the time, and we can read everybody's request. This was in Jetty from September last year to the end of this February. 6 months. There are a lot of people who started developing applications during that time, installed Jetty, and are never going to update. It's going to stay for a long time. And there are a lot of people who updated in that time. This is getting around quite a lot, and it's going to be relatively difficult to notice. Nobody really looks at these errors. This is going to cause a problem. The reason this happened is because the developer who put this in place used a very generic error reporting function that they had available called toDebugString that takes a buffer and gives you a bunch of useful debug information about the buffer. And this is useful debug information. This is great stuff if you're the developer of the application, and this is absolutely not what you want to return back to end users of your application. These are secrets. You should not send them to random people on the internet. What this now does is this. It tells you the character is wrong and nothing else, because that information is not stuff you should make public. Errors really are secret in many ways. This case obviously is particularly bad. What you want as a developer from an error is a message that gives you as much context as possible, and that is really useful from an error, but that is in direct conflict with what you want to send back to your users. You want to give them as little information about your internal implementation as possible. Even if you don't write errors quite as bad as this, it's still very easy to write errors that will expose, say, the fact that this SQL query failed because the syntax is slightly wrong, which makes SQL injections much easier. If you come back with errors giving me detailed analysis of why your validation refused to allow this request, it becomes easier for me to force in requests that you don't want to be allowed, but to get past that validation. The more helpful your error messages are, tragically, the easier it is to break your system. So trying to limit these errors to things that your end users actually need, really helps to limit this kind of problem. And this is sort of the flip side of the input point we were talking about earlier. The developer calling the toDebug string method was assuming it returned a debug string that was widely applicable and that they could just use and return and was safe to return. And the developer writing it clearly knew that it was potentially returning all sorts of crazy secrets. You can't just print the contents of a buffer to the internet. So there's a mismatch, again, in the understanding of the security context of these two bits of information. There are secrets here going on, and we need to ensure that these don't get leaked. Think about your error messages. Be limited in the error messages you provide, and only actually provide extra data to the public that you need to do. And if you have extra information, do sensible, safe things with it. You can log it to log files on the current machine. Hopefully external users can't read those. You can have them, these errors coming back in development mode but not production, and you can be very careful about making sure that's set so that you don't enable development mode in production, which if you look around, there's quite a lot of MVC sites on the internet which will happily do this, and even have warnings at the bottom saying you shouldn't do this in production. This is a really easy problem to fall into, but being strict about these errors will drastically increase the difficulty of every other security vulnerability. You don't just fix individual vulnerabilities here, you make all sorts of breakages much harder. Postgres. Anybody use Postgres? Yeah, loads of people. A few people. Postgres is great. It's a lovely open source database. It does loads of great things. It's really, really good. Everybody else in the room should try Postgres. If you wanted to connect to Postgres, you could do something like this on the command line. This is not going to be a convincing case to try Postgres, but trust me, it's great. The psql command here takes a host you want to connect to and the name of a database you want to connect to. And then it connects you to the database. In probably the most absurd bug of the lot here, it turns out that if you specify a database name that begins with a dash, it is interpreted not as a database name, but as a command line argument to the server. That looks like this. Here we say, write the output of this command on the server to the database. It could be any file we like. We can try all sorts of different file names. If you do write the output of this command, which is an error complaining that you can't log in, if you write this to the end of the database, obviously it immediately corrupts the database. You're not allowed to have random strings attached to the end of your database, so Postgres immediately shuts down. This happens before authentication. This also happens before even connection filtering. Even if in Postgres you say only accept connections from this IP, this works anyway. You can do this to any connectable Postgres. This was live in Postgres from late 2010 to mid 2013. Any connectable Postgres was, you could just turn it off. You had handed the off switch of your database infrastructure to the internet. They're not trustworthy people. We can do worse than this. So the actual error message that we get if, say, the host is wrong, looks like this. This is what we end up concatenating to the end of our database. We can control some of the data in here. We can change the username, and the attack will still work, because it happens before authentication. So we can put whatever content we like in the middle of this. And we can also specify wherever it goes. If, say, we write this somewhere executable, and then get that run on the server, then all of a sudden we can upgrade this from just turning servers off to taking complete control of servers and doing whatever we like. And as it turns out, we can do that. We send a command something like this, and this isn't exactly correct syntax, but you can do it by slightly fiddling the login packets. So we connect to example.com, and we say that we'd like to write to the postgres.profile file. And this will get run the next time the Postgres user logs in. And it's extremely liberal about what it will run. And then we send a username that starts with a new line, and then has a bunch of code we'd like to run, and then a hash to comment out the rest. And we end up with a profile file that looks like this. It's got a bunch of whatever was in there before, and then a bunch of garbage error message, and then some executable code to do anything. Steal all of the database, connect over the SSH keys that you foolishly left on your database server back to the web server and steal everything in there. Delete anything else it can find, steal all the credit card numbers, and so on and so on and so on. And this is very, very bad. And the next time somebody logs in as Postgres, this happens. You do have to wait until somebody logs into the Postgres server. But it turns out, if you connect to somebody's Postgres server and you can corrupt the database, the very first thing the ops team will do is go and log in as the Postgres user on the server, and immediately then you take control of the server. This was a big problem. This is a huge mess, live for 3 years, near enough. Maybe this isn't that bad. Who has connectable databases that you can get at from the internet? As it turns out, loads of people. As of the start of this week, 500,000 Postgres are accessible on the default port. I haven't tried, but I bet a lot of them are running a Postgres release from between 2010 and 2013. There's a lot of reasons for this. Some people are just quite naive, and it's easier to connect stuff up over the internet and just hook it up and go and not worry about it. Lots of cloud services encourage this. So Heroku, for example, gives you a internet connectable Postgres for every single service you start up. Heroku actually have somebody on the board of Postgres and managed to get this patch early and release it, because otherwise their entire business would have been totally screwed. But nobody else did. And this was quite contentious. And the cloud infrastructure stuff all sort of encourages this, but basically anybody who actually does this is in enormous, hilarious danger. And it's not like they did anything particularly crazy. Lots of people will have had passwords on their Postgres instance. They were trusting the authentication of their Postgres instance. But everything fails. At some point, the authentication of your Postgres instance will fall down, and your database will come under hilarious danger, and this will happen, and it'll be very upsetting. You don't need your Postgres to be accessible from the internet. Random people on the internet don't want to talk directly to your database. Certainly, they don't want to do that for a good reason. Isolate your infrastructure from the rest of the web. If you build a nice layered security infrastructure where, say, your database has a firewall around it, then as if your database has a security problem, the firewall is still there. If the firewall has a security problem, your database still has authentication on it anyway. For you to actually have a huge problem, both things have to fail, and that will happen less. If you build these kind of layered infrastructures where you depend on the security of multiple things, you remove any single points of failure for security. All of a sudden, you can put yourself in a position where multiple things have to fail before anything goes wrong. This is much better. Similarly, you want to isolate components within your system. If you're running your database on the same server as your web server, then this is an even bigger problem. All of a sudden, somebody breaking open your database can steal your SSL certificates, can see all the credit card information perhaps that's going back and forth between the web server and your actual users. The problem gets even worse. If you isolate your internal components from one another, you don't have that problem. There shouldn't be any reason why your Postgres server is ever initiating connections to your web server, so just don't allow that. Cut them off from one another completely, or certainly in that direction. You can limit these internal problems and remove a lot of the risk here. If you think about it as sort of bulkheads within ships, if you knock a hole in a ship, the ship does not, or big ship, don't immediately sink. A bit of the ship fills with water and the rest of the ship is fine. You can do this in your infrastructure, and you can ensure that when something does fail, and something will fail, when something does fail, you're in a position where the whole thing doesn't suddenly sink to the bottom of the ocean and leave you unemployed and sad. Bind. Bind is an enormous DNS server. It's the Berkeley Internet Name Daemon. It was invented in the 80s when we discovered that having a single file with every single DNS, with every single name in it, was not going to scale. So it runs 85% of the internet, has a huge market share within DNS servers, and DNS is quite important. If you can break DNS, and we spent quite a lot of effort on various bits of securing DNS, but if you can break DNS, you're opened up to all sorts of phishing attacks. There's, so if, for example, I type in PayPal and I get back the IP address for PayPal, which I get redirected across there and they serve up with an SSL certificate for PayPal, it's very likely I'm not going to notice. Realistically, for the rest of the populace, if you send them off to a new service and it doesn't even have an SSL certificate, nobody's going to notice or care. If you can't trust DNS, you're in a lot of trouble. So this is really important security infrastructure. And we've tried doing things like HSTS and stuff to solve this, but nobody's using it. DNS is fundamental and has to work. Bind does an enormous number of things. Its documentation lists 137 RFCs that define its behavior, plus the actual features they've added themselves. One of the features from these RFCs is Teasing. Has anybody in the room ever heard of Teasing? Excellent. Teasing is transaction signatures for communication between DNS servers. You can think of DNS as a distributed database. At some point, you write to a master, and it has to update the slave. And the slave wants to know the update is really from the master. So we can sign these updates. It's not that popular now because there's things like DNSSEC, which add a bunch of extra security to DNS and solve loads of other problems, including this, in a slightly more complicated way. But still, it's essentially not that useful anymore. In addition, when you set this up, you have to distribute keys. Both the master and the slave need to have a shared key to check that the signature is valid. So you have to copy keys across when you first start the service, and that's a bit of a hassle. There's an extra feature, another RFC for a feature called T-key. which allows you to distribute keys within DNS infrastructure. It's a new kind of DNS record. So I can hit a DNS server and say, give me T key for google.com, and it will give me a key back. And then there's some authentication, some Diffie-Hellman and stuff. But essentially, it lets me go and get these keys so I don't have to pre-share them. This is a slightly weird niche feature for a slightly weird niche feature that nobody's using. The code for this looks like this. This, probably unreadable, but that doesn't really matter. This is an absolutely enormous function written in C, riddled with gotos, switch statements, ifs upon, what is even happening here? Random comments. There's a great bit where we just include all the hex characters for some reason. There's a bit where it says here, this is a hack. This is security infrastructure that runs 85% of the internet. And so on and so on and so on, and down we go. This is one enormous function. It is terrifying, and it is not easy to understand what this does. It's got a major security bug. Anybody spot that there? Anybody imagine trying to audit this and work out what the problem is, even if you know there's a problem? Let's be a little bit clearer. Here is a very specific section of that near the top, where we go and we find the key for a given name. So I've looked up the key for google.com. It prepares a key set and name pointer here, and this is where we're going to put the data. This is C again. So we call find name, and we look in the additional section of the query. And I say, have we got a key matching the name that's in the additional section? And if so, it gets written to name and key set, and hopefully it returns success. And if not, then we find name again, but we look in the answer section, because apparently Windows 2000 is misbehaved slightly. Windows 2000 has a market share of 0.01%, and that is lower than its market share in DNS servers. Like, basically nobody is using Windows 2000, and this is a workaround for Windows 2000 on a feature that nobody uses on a feature that nobody uses. This is code that basically never gets run for a good reason. Spot the bug yet? No. In here, inside find name, we have a whole bunch of interesting stuff going on that's quite confusing. Notably, we require that if you pass in a name pointer to output the name later, it starts off empty. Later, we write to the name pointer. If we found the name, we output the name. Even later, we potentially return success or failure. So we can write to the name pointer and not necessarily have returned success. This code uses one name pointer, takes it, checks if it's not success, and then uses it again. There's a case here where we write the name pointer at the very beginning, we don't return success, and then we call it again with the same name pointer, and it's already got data in. You're right, this is confusing. Critically though, we then hit that require up here, and it turns the server off. It crashes and shuts down. It's like, you're using this completely wrong. Ironically, there's a comment at the top pointing out that maybe this is a bit over the top. All of a sudden, you can turn the server off. This is a problem that has been in bind for a great many years. I'm not really sure. T-key was added in the early 2000s. Windows 2000 has not been around recently. It's basically dead. This has got to be around from a long time ago, and allows you to turn off 85% of the internet. You can send a single packet, and you can turn off DNS. We all depend on DNS for everything. Banks depend on DNS. The government uses DNS for a lot of important infrastructure now. You can turn it off. This is really bad. This is exactly 100% the kind of things that you do not want to happen. There's a lot of problems going on here, but critically, bind is more complicated than it needs to be. It follows 137 RFCs, of which nobody's using nearly all of them. DNS servers mostly need to be able to give you the IP address for a name. Everything else is extra complication. Everything else is extra complicated stuff that makes it less secure. The more things your tools do, the more ways they break. If you try and pick simple tools that only do the things you need, you're in a safer, better position. Less stuff will break, less things will blow up your system, and you will be a happier person. Everything will be more lovely. I'm not just talking about the features here. Bind has a lot of features that do a lot of crazy things. Even the code, though, is quite complicated. This is actually the third rewrite of Bind. The previous versions got too messy. It's getting worse and worse and worse, and actually having a look at the code you used beforehand will help you avoid this. If you take a look at your tools and you look through their code and it's totally unintelligible, there's a good chance that it's quite difficult for anybody else to read, which means there's a very good chance nobody's noticed bugs in it. And some of those will be security bugs. Some of those will be things that will bring your system crashing down and cause problems. If you try and pick simple focus tools that only do what you want and don't have a bunch of shiny extra features that really you're never going to use, you increase your system security. You put yourself in a better place. So those are all the big vulnerabilities I've got in here. I want to make it clear that this is not just all the high-profile vulnerabilities of recent years. All of these has CVE numbers. This is from the Common Vulnerabilities and Exposures database, which is a big standard database of all of these kind of things. And you can go and look all of these up. It's very well organized. All that data is open and extremely accessible. In the last year, since the start of January, there have been 4,500 of these. 711 of them are rated 9 or more out of 10, which means they are extremely easy to do, require no special cases whatsoever, and provide crippling outcomes. These happen all the time, and everything you use breaks endlessly. It's very sad, but it is inevitable, and we have to find ways of actually dealing with this stuff. To wrap up then, let's try and actually find ways of doing this. This is obviously very scary. Security talks aren't fun if they're not scary. But there's a few things we can do to try and limit this kind of damage. Whatever else you're doing, be in a position where you can update. Stuff is going to break. At the very least, you can get the new version of it that works and be safe for a while. Try and be a bit more cautious about user input. Be very careful about who you give it to and what they're expecting of it. Make sure they're expecting it to be insecure if you're giving them insecure data. And generally try and limit the input you accept. You don't need to take anything from anybody. You can be very specific. Best practices are good things for security. They're good things for adding business value. You build better products. It's not just easier to develop. It's not just nicer to develop. The output is better. Errors don't need to expose all of the internals of your infrastructure to the world. If you expose those details, your system is easier to break. Even if you're not exposing that much, every extra bit of information helps attackers. Trying to limit that information, keep stuff internal, turn off development errors in production, all this kind of stuff, drastically reduces these issues. Your components should be isolated from the world and one another. We can build bulkheads, we can build stronger ships, and we can put ourselves in a position where you don't have a single point of security failure. And finally, wherever you can, try and avoid complicated things. Complicated things have more bugs. Some of those bugs will be security bugs. Stuff will come crashing down. Pick simple tools, write simple code, and you'll be in a better, safer position. That's everything I've got for you today. I am Pim Terry on Twitter, and I'll be putting these slides up later if you want to take a look at that. And I work for Softwire, and we're hiring and also for hire. So do come and talk to me about that later. Thank you very much. I think we've actually got 2.5 minutes left for questions. Anybody? What was that, sorry? Yes, so there was a bug fixed in the middle of August. Anybody see, I'm not sure how you say it, RYUJIT, the new optimizer in .NET 4.6? I looked this up because I know there's a lot of .NET developers, which has a bunch of optimizations, and some of them don't work, as it turns out, and you can call a method with some parameters, and it can get different parameters. And if you call that method, and for example, it's turn off production errors in development errors in production, and you pass true, and it actually passes in false, then obviously you've just exposed loads of things. If it's like turn on passwords and it passes in false, similarly you're in a big problem. And there are a whole bunch of proof of concept exploits that break stuff. Like 6 or 7 CVE numbers, they're quite good. CVEdetails.com has a very good database that you can search by product and by month and go and have a look through all this kind of stuff. Yeah? That's a good question. We do a bunch of open source stuff internally, and I organize all the open source stuff internally. In fact, a quick shout out for 24 pull requests. Anybody heard of 24 pull requests? It's an excellent campaign trying to get people to do 1 pull request a day through the 24 days of Advent up to Christmas. Spread the holiday cheer with open source, and I highly recommend it. Any other questions? I think that's a lot. Okay, thank you very much. Do come and grab me later if you want to talk about stuff. I'll be around today and tomorrow. Thank you.